Okay, so the area under the graph is given by this function here between 1 and 9. So we're calculating the shaded area. So we're going to use Simpson's rule with 4 intervals to determine an approximation for the area. Now, because we're using Simpson's rule, you're going to need to go to the formula booklet and look for the one that has got Simpson's rule in there. You'll see that it's got something similar to this. So an approximation for the integral can be given by w divided by 3, bracket, your function with your start value substituted in, plus 4 times your function with the next one added in, plus your function with the next one added in, but like alternating. So, you know, you get me. Yada, 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 plus 2 times the other values that would be in that function, plus yada, yada, yada. You've got the formula book in front of you, or you should, so you can tell what it says. So this one here should be that should be xn, and this one should be 0. Okay, so to work this out, I'm going to first work out the width of the bands. So 9 minus 1 will help me work out the distance of the band, and then I'm going to divide it by how many sections I've got. So here it tells me determine an approximation for the area with 4 intervals. So we're going to divide it by 4, which will give me 2. So W is equal to 2 in this case. So now I've got 2 over 3. Okay, so that's going to be our first part for the approximation here. Now here you can see that you need to have all of these other values. So this one here, when x is 1, that's my initial. When x is 9, that's my last one. And I'm cutting it into 4 bands, meaning each time that it's increasing by 2. So my next band will start at 3. The next one will start at 5. The next one would start at 7. Okay, and you can see from here I've got 1, 2, 3, 4 bands. Okay, so now I'm going to have, for my first one, it's the function with 1 added in, plus 4 lots of, so that's this one here. Now, to figure out what goes in the next bracket, it's the next one and the next one. So 4, bracket, your function when we substitute in 3, plus your function when we substitute in 7, plus. Now, I'm stopping there because the next one here is the last one. So then it's going to be plus 2 times your function at 5. We only have one term in the middle here to include in that section, plus f of the last one. So to figure out these values, I'm just going to type up a little table here. So these are the x values, 1, 3, 5, 7, and 9. And this is what it's going to be when I substitute it in. So remember, I'm substituting those x values into this equation here. So for the first one, I'm substituting in 0.2 e to the power of negative 0.2 x, where I change x to be 1, and each time I'm changing those values. So let's get our calculator up and start typing these. Now I'm going to use the table because I know I can go back and just change values each time. So in my little mind, this is working out to be a faster process. Where is it? Negative 2, bracket, 1, bracket, execute. So there you go. Our first one, oh my God, is going to be, the computer is driving me nuts. Where did that thing go? Okay, let's put that over there. And then we want this one to come up here. Cool, or don't appear, whatever. Where is it? Why did it do that? Okay. So this one is going to equal 0.16 and then the 3 will make that stay as a 3. The next one, I'm just going to go back up and change that formula. So now that's a 2, execute. So now it's 0.13. Again, go back, change the formula. Sorry, that number there that I've just put in is incorrect. I should have substituted in 3. So this number here should be 1, 1 when I apply rounding. Go back, change the formula. So 0.07. Go back, change the formula. .049, go back, change the formula. So last one is going to be 0.03. Okay, so now that I've got all that, I can chuck that into the formula that I calculated that first time. So 2 over 3 bracket. Now, this one's the first one, so 0.16 plus 4 times those middle values. 0.11 plus 0.4. I don't know why that's the only one I've gone to 2 decimal places. We'll round that to 0.05. Close bracket. Plus, now the next one, which is 2 times 0.07, close your bracket, add in that very last one, plus 0.03, close that bracket up, press execute. So now we've worked out that an estimate for what this thing is 0.64, and it would be 6 repeating, so approximately 0.65 units squared. Okay, so that's the estimate that we've come up with. Oh my God. Okay, so next one that we're going to look at, we want to use a calculus approach to evaluate the reasonableness of our approximation. So we're going to be testing that when we integrate this function between 1 and 9, we get something similar. So I'm going to do that in my calculator using the option calc integrate. Now it's still using a calculus process to do this if I'm putting it into the calculator. There we go, and that equals 0.65 or approximately equals 0.65 units squared. So it's important here when it says to evaluate the reasonableness, you need to also make a statement. So therefore, Simpson's rule gives a reasonable estimate as the exact integral, or definite integral is probably a better way of saying that, gives the same answer. All right, and that's it.